So this is our team. Vito, do you want to introduce yourself? Vito? You're on mute, buddy.
Sorry. Hello, my name is Vio Canella. I am a computer engineer, and my role in this project is programming and app design.
I'm Jason Chan, computer engineer and team leader. I'm also programming and designing the app for this project.
Hello, I'm Roberto Battistoni, and I'm an electrical engineer, and I'm working on the circuit design.
And my name is Alexander Van Vollenhoven. I am an electrical engineer, and I have been working on the circuit design.
And the four of us are working under Dr. Paul.
This will be our outline for our presentation.
As concerns regarding climate change continue to grow, people look for individual ways to contribute to the planet's health. One such solution would be the cultivation of plants, though their caretakers may be unaware of their necessities. The purpose of this project was to design an electronic probe by displaying how well the plant's needs are met. This product will not only offer flexibility in the incorporated sensors, but also informative monitoring by collecting data regularly and interpreting trends to provide helpful feedback.
So the need for this product is that there are no effective ways of verifying your probe outputs from sensors that currently exist on the market for measuring quantities such as moisture, pH, and light. And furthermore, if you do buy one of these systems, how do you know that the data that you're getting is accurate? That's where Grow My Data allows you to verify the outputs from your sensors. So the mission of this project was to create a product that was better than those in the marketplace by adding new innovations to enhance performance and enhancing life expectancy of the product by allowing for replaceable components and allowing the user to know when they need to replace a component and what specifically to do in that situation.
So these are the features that we intend on having in this product. So the main features, of course, to allow people to monitor their plants, either when nearby or on the go, attending their business during the day. So while you are out attending your business, the probe will be in your plant, measuring, recording, and analyzing moisture, temperature, sunlight, and humidity data in a user-friendly, simple way. On your phone, you will have an app which the probe is connected to. It'll send the data to it, or you can see the data in the form of, for example, a CSV file, or you can very easily see data spread out over time in the form of tables, diagrams, so that you can see how these things like moisture and temperature have changed over time, and so that you can adapt the way that you take care of your plants in response to that. Additionally, on the market right now, there are a number of different, could you go back?
Yeah.
Yes. Could you go back one step? Thank you. Right now on the market, there are a number of irrigation systems you can buy, which work, for example, over Bluetooth. So that's going to be, for example, like a very simple little pump, which is connected to a water source, which when given a signal will water your plants for you. And we want to have it so that our app is compatible with that, so that not only can you control that watering from your app, but since you can also get that feedback on moisture and humidity data, you can also get a much deeper insight into how much you should water your plants, and which will help you do better with them. Additionally, we want to have it so that the probe itself has multiple sensors for each value, meaning that if one of them for example, breaks or produces for any reason an inaccurate measurement, the probe itself will realize that because it no longer matches the rest of the measurements. And it will then tell the user that a certain sensor needs to be replaced, which the user can then easily do.
So predominantly the market is currently dominated by resistive style measurements, cheap resistive style measurements like this probe right here. And as you can see, there's two prongs, and it usually measures the conductivity between the prongs. And so for a system like this, where you place it inside the soil, you don't really, over time, your measurements become less and less accurate, because as the exposed metal oxidizes, you constantly have to recalibrate it. And for an analog meter like this, that's impossible. And what you end up having is, for a lot of these products, like the Yo-Yo Max, the Iomi Smart Plant Tracker, you have to throw them away after a while, because the entire probe goes once the resistive measurement elements go. Whereas with Grow My Data, we are relying on capacitive measurements.
This is the engineering marketing trade-off matrix. On the left, we have the market requirements for the probe. The smart probe must be durable, it must be cheap, it must return accurate readings, must be easy to use, and it cannot be intrusive, where intrusivity encompasses things like heat radiation, noise, and maybe even a garish appearance. Along the top are the engineering requirements, which are power consumption, the speed of the data processing, the size of the smart probe, and its environmental impact. A durable probe is typically bigger and made with stronger materials, which means more must be harvested from the environment, increasing the environmental impact. An expensive probe will be more power efficient, fast, and compact. Accurate readings take more power, time, and complex circuitry to obtain. The circuitry increases the smart probe size, and the materials increase the environmental impact. A probe that's easy to use must consume less power so that a frugal customer does not struggle with power allocation, and it must be fast to minimize frustration. An intrusive probe consumes more power since it gets wasted as heat or noise, is bigger such that it takes up too much space next to the plant, and harms the environment through this radiation. This is a table displaying some of the microcontrollers we had considered for our project, along with some of their key parameters: flash memory size, number of input-output pins, maximum oscillator frequency, the number and size of their analog to digital converters, compatible interfaces, the cost, the programming language or IDE, and their power consumption in the active mode. The first microcontroller is italicized and highlighted because this is the one we ultimately selected. Through an analytical hierarchy of these parameters, as well as the parameters against themselves, the AD converters became the most important aspect because they are necessary for retrieving data from the sensors. The interfaces were the least important aspect, mainly because we do not expect to use all of the available interfaces. Overall, the large 512 kilobyte flash memory and the 16 12-bit ADCs of the 1891 SAM3X8E drove us to select it, as seen in its highest score.
In this portion, we have used matrices to determine the basic temperature and humidity sensor that will be used in this project. The temperature and humidity sensor used in this project would be the DHT-II basic temperature humidity sensor. The way it was done is through the weighted values matrix, in which I gave every sensor a weight of 0.25 because each is important, and I rated them from a 1 to 3 scale, in which 1 is the best and 3 is the worst. Despite the humidity accuracy, this DHT-I basic temperature humidity sensor has a low cost, is more available, and has a very good temperature accuracy. So that's why I picked that's why the group picked the the DHT11 basic temperature humidity sensor. For the moisture sensor, it seemed very obvious that the 4026 Adafruit would be the one based off the cost and the availability. As seen here with this weighted values matrix, the 4026 Adafruit scores really well with cost and availability. It costs less and it's more available. Thus, we chose this Adafruit. So,
in addition to cost and availability, the Adafruit sensor is relatively easy to be replaced. As you can see, it only has 4 pins and can easily be replaced through a header and embedded into the soil fairly easily. And the capacitive measurement system of it prevents degradation over time and oxidation of the actual measuring elements. This is a picture of our test probe that we hooked up to an Arduino to acquire measurements to actually test the Adafruit stemma. And this is our test code, and yeah.
So the parts that will be used in the creation of this device will involve the Adafruit 4026 stemma moisture sensor, the Adafruit 3955 stemma connector, the Adafruit 386 humidity sensor, the Arduino Duo ATSAM3XAE evaluation, the Raspberry Pi 3 Model B, the Vishay TEFD4300 photodiode, and the Vishay TEFD4330F photodiode, and the Adafruit 1085 16-bit ADC.
This is our preliminary design for the app interface. This is the home screen of the app with a list of your plants and their most recent measurements concerning light, soil moisture, humidity, and temperature. The colors indicate how well this need is satisfied, with green being a good amount and red being too much or too little. You will be able to tap the water icon to activate a water pump on the smart probe, as well as a continuous reading mode so that water is added until the moisture measurement is satisfactory. Next to the measurements is a picture of the plant that you can take, a name that you can set, a favorite marker, and the remaining battery power and network connectivity of the smart probe. On the side menu, you can navigate to other pages. The user page is where you can configure your username, password, and email address through which you might request files of your plant data. The plants page lists all of your plants more concisely, displays the reading per sensor, allows you to manually sort them, and shows you an album and timeline for each plant if you have taken multiple pictures over time. The analysis page is where the graphs can be seen, either showing every parameter for one plant or every plant for one parameter over time. If we have time, we can implement a full plant database with details about every type of plant. Otherwise, we'll have a page providing advice based on your plant data in addition to general plant care tips. Finally, the settings page is where you can configure things like the periodic reading rate, automatic plant sort options, automatic watering, the smart probe name, and notifications. This is the sequence diagram describing the interaction between the app, the smart probe, a server, and the database. First, the probe must be connected to the server, but since the probe has no buttons, the app must be used. The app connects to the probe via Bluetooth and sends it the desired Wi-Fi network ID and password. The user then logs into the server so that the smart probe is associated with this particular user using the Bluetooth connection as verification. Once the smart probe is synced to the server, the Bluetooth connection is severed, and the probe can upload measurements without needing to be open. When the database receives data, it is automatically organized and analyzed to update the related graphs and tables and prepare feedback. The user can then see this on the app at any time. However, when the user wants the actual files, the server can either transfer them via email or prompt the user to open them in a local spreadsheet viewer like Google Sheets or Numbers for iOS users. Manual watering is usually done through Wi-Fi, but it can also occur through Bluetooth if necessary.
So the overall project diagram will involve this. So the user will use their phone. And so before they begin using the app, they first need to create an account. So they must create an account, and it goes from your phone to an email, and it's supposed to verify the account. And then once you verify the account from the email, then you can gain access to the app. Once you gain access to the app, you'll be greeted with it'll start measuring the probe on the plant, and then once it's done that, uh, it'll use this. The way it does that is through the smart probe. You have which involves using sensors, which collects the data, which sends it to the microcontroller. Also, controlling the microcontroller is the wiring systems, which will wire the plant when the user tells the app to do so. Once it does that, it will then take the data and brings it to the computer, and from the computer it'll hook up to a server, and from the server it'll do a bunch of algorithms, and then it returns the data, and then it'll return the data to show the user that, like, through the app and through a .csv file, and it will show the user ways to improve their plant. So now this data flow diagram details how the server will work. So like we have so the way it works is that you have the microcontrol data, right? It returns the readings, it gets the readings. And then at the measurement database, it will analyze the data and returns the data to the database, and then will then do a .csv request from the app, and then it'll open the file in a local spreadsheet viewer, and then the user will be able to seek if it has a little moisture. If it does, in that case, you'll get a request from the app to say, hey, this plant does not have enough moisture, so maybe you should try watering it, and then it'll tell the user to water the plant. So and in order to gain access to all this, you need to have a successful user login, and you must verify by doing that, you have to verify the user and password from the app. This data flow diagram shows how the app will work. The user will go on the app, and the user will be able to go to the settings to either take a picture or select a favorite. And the user will be mostly in the home menu. And to refresh the readings, you just hold on top of the page, scroll down, it'll go back up, and then it will refresh the data. And at the home screen, you can just press the water button, and thus it will connect it through Bluetooth to water the plant. And also from the home screen, you'll be able to access data. You'll be able to access the data from the database and get an analysis of the probe from the probe outputs from the database to gain some tips on whether or not to improve watering your plant or not. And this is how the user will be able to use this device. You'll have this person that will be interactive with GrowMate data. They have to create an account. The measurements will be stored. It'll record the measurements. It'll water the plant through a Bluetooth watering station. It could be like a hose that's connected to the pot. And then you'll have settings adjusted in which it'll take the picture or it'll select your favorite plant. And if you want to really look at this in a state machine diagram, you could see it through this diagram in which the person would just go through GrowMate data if they want to access the app, and then it would be able to enter the app menu. And if they want to exit the app, they'll be brought back to the home menu. And then from there, it'll be able to record data, store and be collected into this database that will be done through servers, and it'll analyze the data, analyze the data, and it'll start creating the graphs and charts, and it'll show it to the user, and they'll be able to determine whether or not they want to export the .csv file. Pretty much, you can water the plants, take pictures, and select a favorite plant. Though pretty much this state diagram pretty much shows you how this app will work.
So here we have the cost estimation for our project. As you can see, it includes all the different components we've used, including the different sensors, the microcontrollers, as well as other components such as op-amps and ADCs. Now, this is a preliminary cost estimation for a few reasons. Mainly, one of the main things that we are currently working on with our current prototype, but which we intend to change, is the fact that we currently have two different microcontrollers, one which is connected to the network and which transmits the data over Wi-Fi and Bluetooth, and another microcontroller which actually runs the code and processes the measured data from the sensors. However, with future prototypes, we want to cut this down and reduce it to just one microcontroller, which handles both of these tasks, which, as you can see in the cost estimation, will also reduce the price by quite a lot. And here's our project timeline. As you can see, we have all of our work mapped out from the beginning of the semester to the end of the next semester, including all these different parts. Now, as you've seen, we've already ordered most of our parts. We have a functioning prototype. So what's left to do is probe construction, implementing a Bluetooth irrigation system, developing the app interface, and then, of course, a stage of testing and improving bug fixing and whatnot, all leading up to our final presentation at the end of the next semester.
So the IEEE ethics that we'll be following for the creation of this presentation will involve decisions that will be beneficial to the safety, health, and welfare of the public. And the team will show any environmental factors that can harm the public. The team will be honest and realistic in claims and data from the project. The team will accept any criticism so that errors can be corrected and credit be contributed to the correct individuals. The team will avoid injuring others' property, reputation, or employment by false or malicious actions. The team will treat all persons regardless of such factors as race, religion, gender, disability, age, or national origin. The team will assist each other when they need help in professional development and following this code of ethics.
And here we have our list of what's left to do for our future works. So our first priority is to create the app, which is going to be the user's interaction with the probe. This means designing the app interface, as well as all the programming that goes behind the scenes in terms of having all the data show up in the right place and in the most user-friendly way possible. We also want to develop the database where all the measurements from the sensors will be saved and processed so that they can be seen in, like we said, in the form of a simple diagram or a table. We also want to develop the server, which is going to be the main hub for connecting all the different parts, the probe to the app, and whatnot. We also want to design probe circuitry. We need to combine all the different sensors with the microcontrollers into the most efficient design possible. And finally, condense that circuitry into one actual probe plus a casing around it, seeing as we do want this to be resistant to any elements, seeing as it might be placed outside. And we also want to finally implement the watering system.
In conclusion, this project will include elements of electrical engineering, such as building the probe circuit in a compact manner to fit within the size constraints, minimizing power consumption, and also being safe and not exposing plants to direct currents. In terms of computer engineering, we'll need our project to be able to interface between sensors and microcontrollers, as well as the user interface as well, to provide them with the data that they need. And we'll need to convert analog signals to digital signals through ADCs, specifically for our future light sensors and humidity. And we'll need to convert the digital signals to more precise numerical measurements. And in terms of computer science requirements, we'll need online databases to store the data regarding the user's probes and measurements, and also, account verifications. And yeah.
Any questions?
Yes, I have a question. Okay. How you are going to calibrate physically your sensors? Calibration procedures? You see, you're using a humidity sensor. This needs to be calibrated.
Yes, we are going to be using humidity sensors. Oh, sorry. We'll be using humidity sensors, and the way we're going to calibrate it is by editing the code within the sensor so that like it'll be able to detect numbers, so that like it'll be able to detect a certain variable.
This is computer calibration. I'm talking about the device itself to prove that you have meaningful measurement, you know?
Yes.
So that's
My suggestion is what I did in the past is to use already a commercial available sensor or to borrow with the readings. Maybe in chemical engineering they have one, you know, or else, and then associate your measurements to that device to find a calibration scale.
I believe that that's the route we will be going down for these sensors.
Because without calibration, you know, this is very important part of your your project, you know. So this is very important. Calibrate your sensors.
Yes.
One feature we have which will help with this is that we have multiple of each different kinds of sensors. So for example, for moisture, we have two different sensors measuring it at the same time, meaning if one of them becomes uncalibrated, then the two measurements will start diverging, which our code will recognize and will tell the user that there's something off about the sensors.
Yeah, this is different. What are you talking? I'm talking about the to check the accuracy of your sensor, you know. So we have to do some absolute measures that comes from a device itself, which has been tested, you know. So the best thing is to use the sensor itself, which, you know, with proven accuracy, which is used commercially, and then compare its readings with your reading. That is the way to go. Hope to solve this problem, you know. Try to check out calibration of humidity sensor. There are a lot of material available, but also keep in mind humidity sensors, there are several chemical parameters and physical parameters that affect the humidity measurement. Keep in mind this, okay? So acidity, for example, acidity, how acid is the, you know, the soil, how other parameters can affect the humidity reading. That is the point. So that be checked with the calibration procedures, please. Otherwise, it's a good study.
Thank you.
Thank you.
Please note those things, students. We need to do this. Okay.
Okay.
Very good study.
Thank you, Dr. Giakos, for the
Very
valuable
good. Very good. That's as important the calibration procedure when we are talking about this kind of sensors. You know.
Yes, yes.
So there are procedures where you have to do it. Yes. Okay. Thank you very much. A good study. Thank you.
Thank you, Dr. Giakos.
Thank you, Dr. Yakos.
Thank you,
Thank
Dr. Yakos, for your.
Thank you.
Any other questions for us?
If not, we'd like to thank you for giving us this time, and
Thank
that will
you.
be the end of our presentation.
Thank you. Thank you.
Presentation.
So please follow all the valuable feedbacks, okay, to improve your projects.
Okay.
And thank you for your hard work.
Thank you for